Have you ever wondered how to replicate the roof design of the Google Bay View campus, which was created by Bjarke Ingels Group and Heatherwick Studio in close collaboration with Google? In this video, we'll show you how to use both Rhino and Grasshopper to achieve a similar result. Our process will begin in Rhino, where we'll generate a 2D diamond grid. From there, we'll move on to Grasshopper, where we'll transform the shape into mesh, lift it up, and use Catenary Curve to create roof surfaces with gaps that will form vertical glass panels. Let's get started. This tutorial is inspired by Google Bay View campus designed by Big and Heatherwick Studio. We'll focus on creation of the roof. These are the images, so we need to create a diamond grid. If we take a look at the diagrams, especially this one, the basic shape is a square. If we take one segment of the square, the center, we can extract only this rectangle. Then we'll take the longest segment of the triangle, divide on 5 segments, and based on these vision points, we can create a diamond grid. We'll focus only on this triangle. We'll create the roof with the openings like we have here. And once we finish with this segment, I'm going to use polar array to distribute geometry at these 3 triangles. This is the way how to create the whole shape. First, we need to create a square. I will type command rectangle, starting point of the rectangle. First, we'll need to set the length 40, set width 40 as well. In the next step, we need to create a diagonal in order to find the center point, divide one segment of the square. I will take the square and I'm going to explode it. Once we select the segment, I will type divide, set 5 number of divisions, and using these points, we can create lines in order to create diamond grid. In the next step, I'm going to use curve boolean, select everything, select no for the combined region in order to create closed polylines for each element, and press enter. Now these 15 closed polylines we are going to reference inside Grasshopper. Curve container, right click, select set multiple curves and select all polylines. Close polylines we need to convert into mesh, connect here, and inside we have 15 meshes, but if I use component from the viewer weld, this one, Bearbird join mesh, and select true inside W input or for the weld in order to weld the mesh. Now I'm going to deconstruct this mesh, take its vertices, and I want to lift them up based on their distance to this point here. How we can extract only this point? Let's say we have a rotated mesh like this. In order to extract only this point of the mesh, I will take all the curves and I will going to type discontinuity to extract all the control points. I will flatten the list and place in the component called duplicates. Here you can see 21 vertices of the mesh. I need to extract only those points that are not overlapped, and the points that are not overlapped are only these 3 guys. If we go right click and select call all, in the result we'll have only 3 points that are not overlapped. In the next step, I will place in the graph. So here we have one list of 3 items, and here we have 3 branches or 3 lists. Inside each list we have 1 item, and we can calculate the distances. Idea is to extract a point which has smallest distance to its neighbor points, which is this one. These 2 distances in total are smallest comparing with these 2 or these 2. Here we have the list of distances, and we can use a mass addition to sum all the distances. And let's flatten the list, and we can sort the list of call points based on a total distance. And if we extract item with index 0, we can select the point that we need. So now I'm going to deconstruct this mesh, type deconstruct mesh, extract all vertices, and we can pull these vertices toward this point. Here we have the list of distances, so I will remap to domain 0 to 1. Source domain will be bounds, and once we get all the distances remap within domain 0 to 1, we can use graph mapper. I will connect with the remap values, and graph type will be Bezier. Later on we are going to modify this Bezier curve, but once we get remap values from 0 to 1, we are going to remap once again within domain. So we'll type construct domain. Here we can set from 12 to 1, which means the point which is closer to the attractor point will be pulled up by 12, and the points that are furthest from the attractor point will be pulled by 1. Once we get remap values, I can use them as amplitude for the Z vector, and we can move mesh vertices. Now these points can be used to construct a new mesh. So this will be points, and the faces we can take from here. Basically, you can see here how we can adjust these points. We need to take our initial curves, explode them. So inside each branch we'll have segments of elements, either triangles or squares. And these segments we need to sort based on distance from the attractor point to middle point of each segment. Once we sort these segments, inside one list will be first 2 items. So for instance, let's say this square here, 2 items that are closer to the attractor point will be these 2 guys. And from this we can create catenary curve, and from the rest we'll create a straight lines or straight point line. This will be used on this mesh. Later on we'll use same items, and let's say for this element, these 2 segments are closer to the attractor curve, and for these 2 we'll create catenary curve, and from these 2 we'll create straight lines. Also here as well, straight lines, catenary curve, also here catenary curve, straight lines, here as well. And using that logic we'll create our final roof design. And I'm going to take original curves, explode them, then I'm going to find middle point of each segment, and I'm going to calculate distance from each point to our attractor point. Once we sort the segments based on their distance to the attractor point, I'm going to use cal index, and I'm going to remove indices 0 and 1. I will type 0 and 1, uncheck multi-line data and place it here. Inside each element we kept either 1 or 2 segments, depending is it a square or triangle. If it's a triangle, we remove these 2 segments and we kept only this one here. If it's square, we remove 2 segments that are closer to the attractor point, and we keep these 2. Once we take the items that we have in the output, I'm going to use item index to find what is the index in our original mesh. First we need to create a curve, closed curve from each mesh face. I will turn this off, explode it, and inside these segments I need to select these guys. In order to know what is their index item, these index items we can find here. This is the list, and these are the items that we want to retrieve. Here we have the index numbers, and I will place them in the list item of this list here. All right, we have straight lines from each element, but we also need to create catenary curves. I'm going to join the segments. Inside each branch we are going to have a single polyline. I will extract endpoints. So let's say for this element here we have this polyline. I'm going to extract endpoints, and I'm going to create catenary curve between these endpoints and the control points of the polyline, which is closer to the attractor point, and it will look like this. I'm going to sort also mesh vertices based on their distance to the attractor curve. So I will take vertices and I will find the distances. I'm going to sort them based on the distance of the attractor curve. And here we have item, and once again we can use item index to find what is the index in this guy in original list. So this is the list, this is the index, and here we have the index number, and these numbers we can use to extract items from these vertices. All right, now we can create catenary curve. We have one set of points and we have another point. Let's type catenary curve. So this is one set of catenary curves, and here we need to type the length. We can calculate the distance between these two, and I'm going to multiply with number slightly larger than 1. Okay, if with 1 the line will be straight, but if we bump this slider up, we'll get the line that we need. And also we need another set of catenary curves for the other segment. I will take endpoint and we'll create another one. Okay, and I will double this one here, and this will be placed in the L input of the catenary. All right, once we have all segments that we need, so these two straight and these two from the catenary, we can create a surface. I'm going to join them and place in the same list. Inside each branch, we should have 4 segments or 4 items, but right now we don't have, and we need to simplify each input. And here we have 15 branches. Inside each branch we have either 4 or 3 segments. Now these segments should be sorted in, let's say, one order. Once we place all segments from each element, we need to sort their segments along original close point lines. I will extract middle point and I will use component sort along curve. And sorting curve or curve to sort along will be these guys. And you can see here that in the P input we have 15 branches, in the C input we have 1 branch with the 15 items. This means we need to graph it. If we take a look at I output, we have sorted index numbers. I will use these index numbers to sort these segments. Now this list of these branches, I'm going to divide into 2 sets of branches. One set will be branches that have 4 items. Another branches will be those that have 3 segments or 3 items. And this will be these 5 guys. Okay, for that I will calculate a list length. And we can test if the list length is equal to 4. And let's use dispatch. This is a pattern. This is a list. In the A output, we have branches with 4 items, and here we have curves that are distributed in branches of 3 items. Why divided into 2 separate data? Because these guys, we are going to use one method to create a surface, and for another set of curves, we'll use another method to create surfaces. So for this one, we are going to use component network surface. This one. In the U input, we need to place curves in U direction. In the V input, we need to place curves in V direction. We know that here we have 4 items, so I will type here 3 times in order to have 4 outputs. And this I or 0 index and index 2, we can use, let's say, merge. These 2 guys I will place in the U, and 1 and 3 will be placed in the V input. So this is fastest way to create a surface based on these 4 curves. For another set of curves that are placed in the branches of 3 items, first I'm going to sort them based on their length, and because I want to use 2 shorter, and we can use a rule surface to create a surface. I'm going to sort in order to select 2 shorter curves. In the I output we have 1. In the +1 output we have another, and we can use component rule surface. Sometimes you will get an error because one of these 2 segments are flipped, so we can use component flip curve, and this will be a guide curve. You will get a warning message, but don't bother about this. We are almost there. Now we need to create these vertical flat surfaces. So this part, in order to fill the gaps between the surfaces that we just created. So for that, I will go back here and I'm going to take the segments and I will flatten them. I will place in the same list all these curves. Then I'm going to find middle point of each and I will say, okay, take each point and find me 2 closest point from this curve. Obviously, the first point will be overlapped point, but the next one, the next closest one, will be this guy here. We can extract index numbers of these 2 points and also these 2 curves and place them in the same branch. Once they're placed in the same branch, we can use a loft to create the surface. And this will be used for all pairs of segments. I'm going to type closest points, so this one. So this will be cloud points to search, and points to search from will be also this point but grafted. So each point should be placed in the separate branch. As a result, I'm going to take I output, but don't forget to set 2 instead of 3. So find me 2 closest points. And I'm going to take only index 1 because we know that index 0 is overlapping point. So I will take item with index 1. So this is how we can create pairs of points. But if we take a look at the corner points, let's say this guy here shouldn't have its pair, and this one shouldn't have its pair as well. Only points that their distance to the second closest point is in this range, and this one as well. So if it's outside of this range, they will be removed from the list. This range we can find if we take these catenary curves and extract middle point, and also middle point if we create a straight line from these guys. So let me connect these endpoints, and here we have straight lines. Also we can extract this middle point. We can calculate these distances, and I will use bounds to create a domain. Don't forget to flatten the list, and here we have minimum and the maximum distance from these 2 points, only considering vertical dimensions. So we can test if these distances from the closest points are within this range. I will take the distances from the item 1, so I'll connect it here. So here we have the list of distances, and we are going to test are these distances within the domain. For that I will use component includes, and this is domain to test. As a result we get true and false, and these true and false values I will use to call index of closest points. Let's type call pattern, connect with the pattern, and connect with indices. As a result we get pairs of index numbers that we need to use, and we are going to use a list item to select the segments and actually pairs of segments. If we take a look at the data structure, we have a list of segments. Inside each branch we have 1 curve and 1 polyline. I'm going to clean data tree in order to remove these branches with no items. Right click on E input and check invert. Alright, and now we can join curves, and we know that these curves are placed in the same plane. We can use boundary surface. These surfaces will be planar. Okay, and now we have roof surfaces and flat glass panels. But what I know that here we have overlapping surfaces, these flat guys, because once we search for the closest points for this point, this guy here is the second closest one, but for this guy here, this is the second closest one. So we have overlapping indices which result with the overlapping surfaces. So in order to remove it, we can extract center using area component, call duplicates, and here we can check leave one, and we can use a list item. Okay, I forgot to flatten because this is why it doesn't work. And instead of having 40 surfaces, we have 20. Now we can place all of them inside the same list. Actually, these 2 guys will be placed in the same list. So I will flatten them. And this one will be placed in another branch. So for that I will use entwine, branch 0 and branch 1, remove branch 2. And now we can distribute them in 3 others in order to create full roof. So let's type polar array. This is geometry. Here we need to set plane, xy plane with the origin attractor point. 4 number of elements, and the angle will be by default 2 pi. And this is how we created full roof. Of course, we can play with this geometry if we modify the slider. In the G output, we have 200 branches. But once we use trim tree, we have 2 branches where 0 branch represent roof surfaces and 1 or 0,1 branch represent glass. So we can separate them with the explode tree. In the 0 we have roof, in the 1 we have glass. And in the final step we can create side glass surfaces. Let's take a geometry that represents roof and use bounding box, right click the union box, and we need to orient this bounding box based on these points. Right, so here we have the one with the index 0, and let's here take the one with the index 1 and with the index 2. Based on these two guys, I will create a vector 2 point, and based on this vector we can actually construct plane. So this will be x and the y can be unit x. Once we create a plane, I'm going to use this plane to orient bounding box. Once we set proper position of the bounding box, I'm going to deconstruct each roof surface, and I will extract a middle point of each edge, and I'm going to test whether these points are placed inside the B-rep. So there is a component point in B-rep. These are points, this is B-rep. And don't forget to set true for the inside the strict input, and using this pattern we can call the edges. Here we have the edges that their middle point is placed inside the bounding box, but if we invert the pattern, here we have the edges that their middle point is placed on the bounding box. I'm going to flatten the list of edges, and we can project them on the XY plane. So projection plane will be XY, and now simply with the ruled surface we can create side glass surface. And you can see if I rotate our original curves, the whole geometry will be oriented. And for instance, if I let's say scale this one like this, the whole geometry will be modified. In the extended tutorial, we'll explore how to create the whole shape in Grasshopper only. Rather than drawing the grid in Rhino, we'll use Paneling Tools plugin to create it entirely within Grasshopper. By following this tutorial, you will gain an understanding on the principles of custom panelization and how to manipulate paneling patterns in Grasshopper. Once you have a basic knowledge of paneling tools, you will be able to create more complex and accurate paneling patterns, opening up a wide range of creative possibilities. In addition to that, the extended video will also cover how to add further details such as columns and glass frames to both roof and side facades of the building. You can get access to the extended tutorial on our Patreon page, and with that you will also get access to all of our other extended tutorials and project files. The link is in the description. If you'd like to know exactly how to create complex projects like these, and if you're interested in step-by-step learning approach, starting from zero, make sure to check our Grasshopper Complete course, where you'll find over 60 hours of video material structured in a form of video library, covering in depth more than 500 Grasshopper components through practical examples. And you'll have access to us personally, so we can answer all of your questions right away. The link is in the description.